So, regression. Suppose we have a sample with two measurands, one being the force through a spring and two being its displacement, x, okay? Not from equilibrium, so say some non-equilibrium displacement that we measure x from. We would like to determine an analytic function that relates the variables. Perhaps for prediction of the force given another displacement. So maybe we measure it for like 10 displacements or whatever I choose. I think it's like 10. And then we want to be able to extrapolate like what any displacement force would be, perhaps. Or maybe we want to find the spring constant. These are the types of things we might want to know. So there is some variation in the measurements. Let's say the following is the sample. So we have 10 millimeter displacement, gave us 50.1 newtons of force. 21 millimeter displacement gave us 50.4 newtons of force, etc. Right? And let's take a look at the data. 4.23 is where it's plotted. So this is the data we're working with. It looks roughly linear, right? So we're going to do a regression on it. We're actually not just going to do a linear regression. We're going to do a polynomial regression of a bunch of different orders. And linear is probably the right one to use for this, but we'll have a discussion about why that is, or how you would know. So this is our data. You guys have all done, what's kind of funny is that you guys have all done regression analysis before using that great analytic technique, Excel. Right? Did anybody actually learn how to do regression? Okay, so like one of you learned how to actually do it.
Chemistry, yeah, if you had to.
Maybe.
Cool. Yeah, so some of you may be exposed to this. Maybe this is review for you, which is cool. So here is the data. We saw the plot. This was just me plotting it. I actually have been suppressing this. Once again, the code is available on the website. I'm pretty sure I put the code out on the website. If I didn't, then I will soon. So this is just plotting the data. How might we find an analytic function that agrees with the data? That's the question that regression asks. That's what we're trying to answer. Broadly, our strategy will be to assume a general form of a function and use the data to set the parameters in the function such that the difference between the data and the function is minimal. That's generally our strategy. Let y be the analytic function that we would like to fit to the data. Let y sub I denote the value of y of xi, where xi is the ith value of the random variable x from the sample. When we want to, then we want to minimize the differences between the force measurements fi and yi. So coming back over here, we want to draw some function. Do this. Kind of like my fat marker for that one. But I'm going to switch over to the cool custom library because I guess I like to draw with my own brushes. So this is going to be y. We want to draw y. We want the difference between y and each of these fi's to be minimal in some sense, right? There are a lot of them though. So you got to deal with all of these differences. And you want to minimize those differences. Okay? So, from calculus, recall that we can minimize a function by differentiating it and solving for the zero crossings, which correspond to local maxima or minima. Does that sound familiar? If you take the derivative, then you're finding the slope, right? When the slope is 0, that means that the function has either reached a maximum or it's reached a minimum locally. It doesn't have to be globally minimum or maximum, but, right? Local maximum or local minimum. Yeah. So if we're going to use that technique here, which is what we're going to do, first we need to construct a function to minimize. Okay, so we need a function that we want to minimize. It's not the function itself, y, that we want to minimize. We want to minimize some function that describes the differences between each of the measurements and this function, right? We want to minimize that. So remember, we want to minimize these guys. That's what we want to minimize. So the simplest, or perhaps the simplest, effective function d is constructed by squaring and summing the differences we want to minimize. For sample size n, you take the difference between the measured value and the analytic value, and you square it, and you sum them up. Why do we square it?
What's the difference? Get rid of the true difference.
Well, we do it because if you don't square it, then like if you're above the line a little bit or below the line a little bit, the sign matters, right? So we don't want to have a situation where this difference cancels this difference, right? Because this one's a positive difference, this one's negative. We don't want that. That's why we square the difference, which gives us always a positive value for every difference. We want to minimize that difference. Okay? That's why we square it. There are other things. You could take the absolute value also. The reason that we typically don't take the absolute value is that it is to work with. It's not nice. It's mean. It's like my grandma. Okay.
She's the average of something. The Republican one?
The what?
The Republican one?
Yeah.
The way you said grandma was pretty.
I know.
The story you told when she came and she went to one of the speakers last year and she was talking about it's that's a question.
I'm trying to refrain from talking about her. I feel like I'm going to though, because nothing good can come of it. So recall that if you evaluate that function at xi, that's what we mean by yi. So evaluating the function at xi. Which makes d a function of x. So it's a function, d depends on where you are here, right? Because if you evaluate d at this point, it's this, that absolute value squared, or that squared, or this squared, right? Okay. Now the form of y must be chosen. We consider only mth order polynomial functions y, but others can be used in a similar manner. So using polynomials is pretty straightforward. You can use actually any function, even very nonlinear functions, because polynomials are nonlinear once you go up to second order, right? And so they can be nonlinear as long as, and you can use this method exactly, as long as the only the coefficients you're trying to fit enter linearly. So for instance, A2, A1, A0, AM, they all enter linearly. They're not squared or anything, right? Or square root of AM. None of that. So as long as you fit something, or the other thing that would be bad is, for instance, you could use things like sine, but you couldn't put in an AM in the sine. That would be nonlinear. But they enter linearly. These ones enter linearly, so they're fine. And you can do this with other functions. We'll look at polynomials because it's the most common case, but you can do it with any other function too, as long as your coefficients enter linearly. You can do it with nonlinear case as well, but it's just a lot harder. So, if we treat D as a function of the polynomial coefficients now, a0 through am, and minimize D for each value of xi, we must take the partial derivatives of D with respect to each a value, okay? So you take the partial of D with respect to the first coefficient, partial with respect to the other coefficient, all of those partials. Now, we're taking these partials and setting them equal to 0 because we want to minimize D with respect to all of these coefficients, right? And this is going to give us n equations and m plus 1 unknowns, which are our coefficients. So we want to know what the polynomial coefficients are that fit the data the best. That's the question that we're asking. I mean, the first question we asked is, can we come up with an analytic function that fits the data? But we chose it to be a polynomial, and since it's a polynomial, this is the case, and now we want to know what these polynomial coefficients are that actually minimize this value. So it changed our question, got a little bit more specific. Instead of just come up with a function, now let's just come up with the coefficients, the A coefficients. Now, if we write the system in matrix form, we get this. So what does this say? So let's read off the first line. The first line says that 1 times A0. So A0 plus x1 A1 plus x1 squared A2 plus all the way up to x1 to the m AM is equal to y0. So this is polynomial equation evaluated at whatever my x1 data point was. So back over here, this is my x1 data point, right? So I just pop that in there. The whole first row, I stick in x1 the whole way. So 10 millimeters all the way across, so 10 millimeters squared, all the way up to 10 millimeters to the nth power. Okay? And then I say it's equal to y0. So this is the, essentially this is the data point that came out. So this is my F, my first force that came out. So wherever that was. That one. And so that gave me one equation for all the A's. The next equation, I plug in x2. I am y1. Or sorry, I'm y2. Yeah, that's right. y1, I guess. Because of the weird way that these start at 0 and these don't. Down to ym. And we have then the system that's not square, so we can't just take the inverse of A. So typically n is greater than m, meaning that you have more data points in your sample than you have the order of the system you're trying to fit to it. So if you try to fit a 10th order polynomial to 3 data points, fine, but that's not typically the case. Typically, you're going to have a system that's going to be, you're going to have way more data points than you're going to have order that you want to fit to it. For instance, we want to fit a first order system, right? A linear one is probably what we're going to do eventually with this problem. But we've got like 10 data points, right? So 10 data points is greater than 1. So we have what's called an over-determined system. Yeah.
Not that my linear algebra skills were the best, but shouldn't B be an n by 1 matrix, not an n plus 1 by 1, since the multiplying matrices together the coefficients on the insides have to match, but then you end up with an product being the outside term and then the 1. So it should be a n times n plus 1.
No, because when you multiply A and B together, it's gonna work because
No,
It should be
you
A
have
by
A
1.
times,
N-
yeah, big A times
n, yeah,
one.
b should be n by 1.
Yeah.
You're right.
Because whenever you line them
This
up,
should be n,
Yeah.
the
Yeah.
plus ones cancel.
Yeah, there you go.
and this should be n. So this is an n, or
X
yeah,
is to the n, but
It's an n by 1.
n by m plus 1, and then we're going to multiply that by an m plus 1 by 1.
Yeah, so you,
Inner dimensions me, so we get left with an n by 1.
there you go.
wait.
Yeah.
Trust me, I'm fresh in this.
That's
no, you're
correct.
Right. See, because you overlap them, so the inside ones cancel. Right.
Yeah. Good call. Thank you. That was a typo that entered in yesterday when I was like halfway watching The Office as I wrote this.
You were in the office. You're watching The Office. Okay, please
Yeah.
watch Parks and Recreation when you're done, so that you can see the light.
So I watched the first few seasons of it.
Parks and Recreation.
Yeah.
Yeah.
Or did you
I
stop-
liked it. I
so
liked
did you
it.
stop watching it because your grandma stopped watching
No, I stopped watching it because Hulu got too hard to deal with. I just couldn't handle how many commercials there
They
were.
took How I Met Your Mother off Netflix, so now I have to
Oh
watch
my
it.
god. You don't have the no commercial Hulu?
No.
Oh, it's so good.
Isn't this like your fourth time watching?
Yeah, it's been several years since I used Hulu because I got so tired of the commercials. So.
Just pay a little bit more for the no commercial one.
Yeah, well, if I ever watched it again, I would. I don't know. Anyways, we'll talk about movies and shows later. We gotta do
We're
this.
getting off topic.
Okay,
Back
so
to the n by 1.
so since we have an n by m plus 1 matrix here, you can't take the inverse of this in general. I mean, if it happens to work out that m plus 1 equals n, great. You have a square matrix and you can invert it. But you can't invert a non-square matrix. So you're kind of like stuck in a certain sense, but we're going to find a way through. So there are kind of two ways to go around this. The first is to take the Moore-Penrose pseudo-inverse, which is a dagger. That's how it's denoted. And the pseudo-inverse allows us to have the solution, a dagger b, but it's super inefficient to do it that way, okay? So it does work technically, and you can do it in MATLAB for like small systems, it's fine. But it's not great if you're gonna do more than a small system. We can approximate B with an algorithm such as that used by MATLAB's. It's the slash operator, okay? So this operator, there's a name for the function too, but I'm not thinking of it right now. This operator is easily used. What you do instead of writing like A inverse times BA, instead use A slash BA. So pretty much what this does is it says, it tells you what the estimate of all of the A coefficients are. And this algorithm is much more efficient than actually finding the Moore-Penrose pseudo-inverse. Okay, the Moore-Penrose pseudo-inverse is good for mostly for theoretical stuff. When you do theory, it's great. So you can write stuff like this. But when you actually have to compute it, it's much better to use something like this, which is an efficient algorithm. We aren't going to get into the algorithm. It's a whole thing. But we don't need to go on that. So let's do that. Let's use MATLAB's slash operator to find a good fit for the sample. Now, there's a sometimes difficult question, what order should we fit? Okay. In this problem, I think it's pretty clear that first order makes sense because theoretically we think, spring, it's probably pretty linear, at least in some operating regime. The data looks pretty linear, so we probably should do something like first order. But when you're fitting something that you don't know for sure what it's going to be, or if the data doesn't look very linear, then the question is, well, what function? And that's tough. And if you're doing polynomial, then the question is what order should you use? It really just depends on what you want to learn from the problem. Sometimes higher orders make sense, but oftentimes we try to get away with as low of an order as possible that looks like it somehow fits the data. And what I did was I said, let's try out several and see what the squared difference function D gives. So what I did was I went through and computed these. And it's actually, what I decided to do was take every other order up to n, I guess stopped one before n, because I think n was 11, so it stopped at 10, and it did a fit for that order. So then I ended up with a triple for loop. So apologies for making this look a little scarier than it is, but essentially I'm just computing what my A matrix is. So first we have to compute where was the A matrix? Right here. I got to compute, this is not the same A matrix from system dynamics, by the way. Different. A is just a common thing to use as a matrix. So this matrix, we got to construct this from our data, right? So we got to come in, we got to put our first point in, 1, then 10 millimeters squared, and then the next row is 1, and then 20 millimeters squared, 20 millimeters, 20 millimeters squared, 20 millimeters to the nth power, etc. So that was what I was doing in this. So it's really just this inner loop is doing that matrix. This outermost loop is doing for each order. Okay, so fitting it to a second order system, fitting it to a fourth order system, fitting it to a sixth order system, etc. So I go through, I compute it, and I print out for the second one, I print out the first 5 columns, and we see kind of what they look like. So the other thing that I did was I pre-allocated with all nans, and so I printed out one nan column to show you that that's the only valid one. I'm using a 3-dimensional array here, which I know sounds scary, but one day you'll feel like a 3-dimensional array is no thing. So there are different ways you can go with it. I actually really don't like MATLAB's way of dealing with different sized data so for instance, this was a little tricky because with these lower order ones, I had a bunch of empty nans out here, right? And I could have gone with a different data type. So on a lower dimension, you could think of it as I had different length of rows of data to put in. And so I just filled in this extra space with nans on a lower dimension. And so this is the method I'm using. And it's not great, but it's one way that you can do it in MATLAB. The other one you could do is cell arrays. But I kind of don't like cell arrays.
Nobody likes celery.
Yeah.
Here's one question.
So you can put different lengths of data in cell arrays, which is why that's kind of useful. But it's hard to access it. It's a little bit trickier to access. You try to access and excess, it's a problem. Didn't have another word that was like that. Okay.
Sounds like you're trying to reach the bottom of the peanut butter jar with this phrase text.
So these are just one of the sub arrays I thought I would print out just to show you kind of what it looks like. But you see the ones showing up, and the x values showing up. So this one, so x1, see there's my 10 millimeters, right? 10 millimeters showing up from way back here. What? 10 millimeters. And then the next one was 21 millimeters. There's my 21 millimeters, etc. All right, so that is the data. And now I've got my A matrices, okay? And now, now we can use the slash operator to solve for the coefficients. So I took the warning off so it didn't print off this annoying warning about being an ill-conditioned matrix. It's not a good thing to do in general. If you have an ill-conditioned matrix, it's not something you should just turn the warning off for. But I didn't think it looked pretty in the notes, so turned it off. But see, I turned it back on. No problem. Okay, so this A now is essentially taking this multi-dimensional array and squeezing out the higher dimensions of the singleton dimension, so that it comes down to a matrix. Then I can just do this slash operator. This is the slash operator happening right there. Bam. And then I've got all my solutions in this little a, okay? So what I then do is, so what I have are the coefficients. This little a are the coefficients, all these values. So I've estimated those for these different orders, right? Now I need to plot them. So I do that by using this polyval function in MATLAB. Polyval is a great little function. It allows you to not have to write your own polynomial with those coefficients. It just says, oh, I know you're going to hand me the coefficients of a polynomial, and I'll plug it into a polynomial function of the order corresponding to the length of your vector that correspond to the coefficients. So that's what you do. You had to do this flip left right because my coefficients came out backwards. If you didn't do that, it looked horrible. And yes, that took me about a half hour to figure out. I was like, what? I was kind of reusing parts of code that I wrote 4 years ago. And I didn't do it for a bunch of different lengths. I did a bunch of different orders when I did that code, so it was coming out different, and it was just like hidden in there. So annoying. But in any case, this is what comes out. So we have X, F. We have these different Y's. So I went every other order so that I didn't have too many lines on here because it was getting kind of crazy. But first order is just the linear one, which is the blue one. And that's pretty good. Like, we see the blue one just going kind of straight through the data. That's probably the one we want to go with, right? But I thought it would be interesting to look at what happens when we increase the order. So third order is the orange, then fifth order, seventh, ninth order. And what we see, what's interesting is that there are 11 points, right? Are there 11? 10 points. I think that what it is so if you increase the order to equal the number of points, I think it's the number of points plus 1 or something like that, you can go through every single data point with your fit, guaranteed. Guarantees you go through every one. The reason I didn't do it is that in order to do that, especially this one was really screwing it up because it's kind of a wonky point. It had to create this crazy polynomial that went off. It was going like this, way off the graph through all these points. So it was it made it so you couldn't read the rest of the graph. So I left those ones off. But clearly you don't want to do this, right? Like, so yeah, you could fit this thing to a ninth or to an 11th order polynomial for 10 points, but what you're gaining from that is pretty minimal. And I think that the underlying process is probably not is probably, it's hard to keep a straight face looking in the ear. Like,
Thanks.
derail
It's so
me.
funny looking. That's great.
It's not that you're funny, like, it's just you have very specific faces that are really hard to imitate.
Okay.
Game face.
So, you're like making faces at me up here, and I'm like just trying to
It's just my face.
keep it together.
Do you want a paper bag?
Sorry.
Okay.
Moses coming off Mount Sinai.
So
Your bag.
you can go to these higher orders, but what are you gaining? You can predict exactly what value the function should have at that point, but is that somehow showing an underlying model? Probably not, right? Because you have random variation in your samples. Your samples aren't exactly on some perfect value. So probably you don't want to fit these to some higher order model. And actually what it's called when you get to these higher orders than you need, we call that overfitting. And this is a big topic in machine learning, for instance, because a lot of machine learning is done with regression models. And if you overfit, what happens is you actually come up with worse predictions. So it's like you have an effectiveness, you could think of like an effectiveness curve where as you fit, so I'll kind of draw this up here. As you fit from lower orders to higher orders, usually it's effective at predicting things. It's better and better. And then when you start overfitting, it goes down. And so there's this sort of sweet spot in here. For us, the sweet spot is like first order, okay? That's where we want to be. But, because if you went to 0 with order, that would be a straight line like this. You probably don't want that. A flat line with 0 slope. Probably don't want that one. So that would be corresponding to like right here. You peak at 1, and then you go to higher orders, and the effectiveness at predicting something is probably going to go down after that. So overfitting, so this is overfitting.
Is that just because you don't, like with a straight line, you know exactly how it's going to behave past the graph points, but the overfit things will just behave by whatever point you put on the graph?
That's part of it. Extrapolation to points outside here is really bad with the higher order ones.
Right, because there's no way to know. If you put another point on there, it would just behave in a way that it would try to fit that point, no matter if the point was garbage or not.
Right, like for instance, that green one probably goes up like this. And it's very unlikely that these next data points down here would actually go up there, right? That's part of it. The other part of it is that there are these predictions that we're making are based on a finite data set, right? So like for instance, if you like took away a few of these points and you said, or like if you zoomed in, let's just zoom in. Let's look like between this point and this point. Technically this curve works, and technically this curve works. There's a lot of curves that work, right? They go actually like perfectly through these points. But we don't know, we only have these 2 points, and it's not good to take too much stock in the points that you have, right? We don't want to take too much stock in them. We don't want to say, oh, that one's definitely true. Like for instance, with this outlier here, potential outlier here, this one's probably just, it was not a very good measurement that we took. And this value probably shouldn't affect our model too much. But if we're too sensitive to that type of thing, and we overfit this, then, your prediction might come out to look something like that for that region. But that's probably not good. Probably the data is actually in here. and it doesn't go way up there. So it's like you could take too much stock into each point you have and overfit. So there is a lot that goes into this. Whole textbooks are written on fitting, overfitting, and you can delve into it. But machine learning uses these regression techniques to determine, if you have another point in here, like approximately what should I predict to come out. And so it'll do these different orders of regression, polynomial or other types of functions. And determining what's best is, at this point, still kind of an art. There are different algorithms that can help you with that. They're not as susceptible to overfitting, but sometimes it's hard to avoid. And a lot of times it comes down to having a person guide stuff still by saying, I think this is probably second order, third order, based on some prior knowledge of the system. So yeah, and that's what we, like for us, we're not trying to come up with an automated algorithm to do the fitting, but we're just trying to look at some data and predict, for instance, for the first order system, I didn't print it out, I was meaning to print it out, what the slope is. Like maybe we want to know what the spring constant is. The spring constant is just the slope, right? So maybe that's what we cared about. And that's the type of thing you guys probably did in the physics lab when you used this. And so yes, you can plug this, you can do this in Excel, and actually MATLAB allows you to do this much easier than the way that we did it. We rolled our own on this one, but for the most part. But this allows you a little bit more flexibility. Like if you needed to fit to another function that wasn't polynomial, a lot of times there aren't, they don't have that function plugged in as into Excel. You can only do polynomial fits, I think, in Excel. And so you could come up with your own series and your own coefficients to fit with, depending on the situation. So it's useful. It's good to see this once because I know that it's really common for you guys to use curve fitting stuff. And MATLAB has like curve fitting stuff. You can just pull up and you plot something. You can just like right click and add in a curve fit, right? Who's done that? Nobody's done that yet?
Yes.
Wait, what?
If you just have a plot with a bunch, like, so if you had this original plot in MATLAB, you can just in that figure window, you can pull up the plotting and statistics
I do that all
thing.
the time.
Yeah,
I
and you
don't mess
can,
with polyfit, polyval.
yeah.
It's too complicated.
So
Things go weird.
you can
I
do
know it
that.
now, but I didn't know how to do it.
When you first learn, I think it's good to be able to use those tools, but I think it's good to understand how it works at a deeper level. So like for me, if I'm gonna do a linear fit and I have just some data and I just want to put like a quick and dirty, what's the slope of this best fit? I'll use that in MATLAB too. I don't go back and look at the polyval function every time. Like that's not the easiest thing to do. But there's also a function polyfit in MATLAB which allows you to do a lot of this without having to go through the derivation that we did. But I thought it was worth showing you how it's done in case you ever need to fit a different sort of function. So this is regression, and that does conclude all the statistics that I'm going to do. Unfortunately, that's all we have time for. But look for this lecture on the website. The source MATLAB will be up there.
Have a good Thanksgiving.